Hello everybody, welcome back to another Gregorius Maths video. Today, and this t-shirt is amazing. Unfortunately, this merchandise is not for sale yet, although hopefully I can persuade my parents to put it on sale, because I'm sure you'll all buy a t-shirt. But anyway, today is going to be an algebraic extravaganza, and it's going to be a contour integration example, but I can't take the credit for this. This was thanks to Wikipedia, so please do check out Wikipedia. I was reading this on the bus on my Nokia 3310, and I thought, hey, why not make a video? It's a good example. Yeah, do check out Wikipedia for their maths. They have a really wide range of topics in maths as well on Wikipedia. Anyway, enough talk. What will I actually be doing? The integral between pi and negative pi of 1 over 1 plus 3 cosine of t squared dt. And today we're going to be evaluating this real integral with trigonometric functions using contour integration. So first, let's write some stuff down in red. Even though all substitutions are in blue, my blue pen's running out, so I'll use red. Let z equal e to the it. Why am I doing this? Well, if we recall, cosine of t equals 1/2 e to the it plus e to the negative it. Okay, hence why I'm doing this. And let's just do dz is therefore equal to I times e to the it using the chain rule. But this is dt. Oh, I need to put the dt. But this is just z. Means that dz equals iz times dt. But we can divide both sides by iz, leaving us with this. Okay. Now let's plug all of this new information in. What are we left with? I forgot to write one of the most important things in this video. C. Our contour integral is going to be C along C, which is we're going to define to be the unit circle. Unit circle. Not the unit circle factorial, just exclamation mark as an important notice. Okay, so now we're going to transform this into a contour integral. So this equals the contour integral of 1 over 1 plus, okay, squaring this leaves us with 1 over 4. So 3 times that leaves us with 3 over 4. Okay, and then z plus z to the negative 1, which is 1 over z, squared, times dz over iz. Well, 1 over I, we can bring that to the front, which 1 over I equals negative I, if you just multiply the top and bottom I. And we can bring this 1 over z down to the bottom, so we're actually left with z plus 3 over 4 z times this, dz, which equals negative I times the contour integral of 1 over, now, let's expand this whole thing out. Z, I'll just do this on the side, z plus 1 over z squared equals z squared plus z times 1 over z times 2 plus 1 over z squared. Well, z over z becomes 1, so we actually just left with z squared plus 2 plus 1 over z squared, okay? Right, yeah. So we're left with oh yeah, let's see, of z plus 3 over 4 z times z squared plus 2 plus 1 over z squared dz. Yeah, okay, I'm going to have to switch markers. I might have to switch back to black, honestly. Okay. But now distributing this z in leaves us with negative I times the contour integral of 1 over... I'm going to leave this z for now, so we're going to get 3z cubed over 4 plus... C. Here's what we get. This is a 2. Okay. So, plus 2. So 3 over 4z times 2 leaves us with 6z over 4. Correct? That becomes over 2. That becomes a 3. But now when we add z to this, that's the same as adding 2z over 2. So this becomes actually 5z over 2 plus 3z over 4, no, yeah, 3 over 4z, yeah, okay, that's right, dz. Now what do we want to do? We want to get rid of all of these ugly fractions. How do we do that? Well, hopefully that's not too difficult. Just multiply the top and bottom by 4z. Okay, what does this leave us with? This leaves us with, well, this 4 on the top, we can bring that to the outside. So negative 4i times the contour integral, okay, let's make space, of z over 3z to the power of 4 plus 10z squared plus 3. Yeah, okay. dz. Why did we want to do that? Well, we can factor this quite nicely to calculate the residues a bit easier. You'll see what I mean soon. Okay. So now, let's do this. How are we going to factor this? This here is equal to, so I can save space on the bottom for the last part, negative 4i times the contour integral of z over 3 times z plus square root of 3 times I times z minus square root of 3 times I times z plus I over square root of 3 times z minus I over square root of 3 dz. Okay, I might have to write this dz at the top. Okay. Okay. Why do we want to do this? A, it's easy to calculate the residues. B, we can bring this 3 to the outside. Very nice. So we get negative 4i over 3 times this. Here is where Cauchy's residue theorem comes into play. What does it state? Well, another note. Cauchy residue theorem states that the contour integral of f of z dz equals 2 pi I times the sum of all the residues. Okay? I think I've written that slightly wrong, but basically it's the sum of all the residues. Please let me know how I'll write in the comments how I should have written that. Yeah, okay. So, how are we going to use this? How do we find the residues? Well, remember, C is the unit circle. So, the singularities in C, are plus minus I over square root of 3. Okay? Why is plus minus square root of 3 times I not included? Because those are not in C. Those are outside the unit circle. Because square root of 3 is greater than 1, basically. So now, let's plug all of this new information in. First of all, I'd just like to say that 2 pi I times negative 4i over 3 is equal to 8 over 3 pi. Because all the i's and the negatives will cancel, basically. Just to save space. So, 8 over 3 pi times... yes, okay, we need to define some new stuff to calculate this. Okay, so, let C1 be a small circle centered at I over square root of 3 and yeah, anyway, and C2 be a small circle. Okay, actually, just to save space, I'll say B1. By 1, I mean a small circle. B1 centered at negative I over square root of 3. Okay? So now let's plug all of this new information in. Yeah, okay. So what's our first contour integral? That's C1 of Z over Z plus square root of 3 times I times Z minus square root of 3 times I. Yeah, times Z plus I over square root 3 all over Z minus I over square root of 3. No brackets needed. And dz. Yes, finally I have enough space after all those shots I did yesterday. I have space. Shots I did yesterday were pretty rubbish there. Okay, anyway, moving on. Plus, the contour integral about C2 of Z over Z plus square root of 3 times I times Z minus square root of 3 times I times Z minus I over square root of 3 all over Z plus I over square root of 3. dz. Just yeah, write the dz, okay. And close the brackets, but I don't have enough space. Don't get triggered. I just don't have space to close the brackets. Okay, so we're just gonna, yeah, right. To calculate the residues, what should we do? So the 8 over 3 pi stays the same, but now we can, in this case, just do this. Evaluate each of these Z over Z plus square root of 3 times I times Z minus square root of 3 times I times Z plus I over square root of 3. We can evaluate this at Z equals I over square root of 3. and then plus, same procedure, z over z plus square root of 3 times I times z minus square root of 3 times I times z minus I over square root of 3. And then all of this, I'll just write this at z equals negative I over square root of 3, because I don't have enough space to write this. Okay. Now, final step of working, because I'll rub everything out as I go along. This equals 8 over 3 pi times, now let's plug all of our things in, I over square root of 3 over I over square root of 3 plus square root of 3 times I. Okay, actually, yeah, let's look at each of the brackets individually. For this part here, to get the common denominator, we can multiply the top and bottom by square root of 3. Square root of 3 squared is just 3 over square root of 3. And then we can combine, so we get 4 over square root of 3 times I. So we get I times 4 over square root of 3. Next bracket. I over square root of 3 minus square root of 3 times I. Same procedure. Multiply the top and bottom by square root of 3, leaving us with 3I root of 3. So what's I minus 3I? That's just negative 2I. So we left with negative I 2 over square root of 3. Final bracket. I over square root of 3 plus I over square root of 3. Well, here, what's even better is that I don't even need any fancy tricks. I can literally just combine them because they've already got the same denominator, leaving us with I times 2 over square root of 3. Right, and then this plus negative I over square root of 3 over, okay, same procedure, negative I over square root of 3 plus square root of 3 times I, multiply the top and bottom by square root of 3, leaving us with this. What's negative I plus 3I? That's just 2I. So we get I times 2 over square root of 3. So far so good. Now, next bracket please. Negative I over square root of 3 minus square root of 3 times I. Same procedure. Over square root of 3. What's negative I minus 3I? That's negative 4I. And we can of course combine the denominators. So we get negative I 4 over square root of 3. Now, last one, z minus, negative I over 3, square root of 3, minus I over square root of 3. Well, we don't need to combine any denominators or anything. We don't need to do any more multiplying top and bottom. because the top and bottom are already the same denominator. So overall we just get negative I times 2 square root of 3. Negative I times 2 over square root of 3. Okay? Good, good. Now I want you to observe something. We can multiply this by I over I, leaving us with negative 1 on the top, so negative 1 equals negative 1 over square root of 3 times I, correct? So this is where I'm getting these negatives from, okay? But I can write this in whatever form I want. So this is, just want you to realise that this is equal to negative 1, sorry about that, negative 1 over square root of 3. Okay, cool. So, now, what are we left with? Well, I'll tell you what we're left with. We're left with, when we factor the I out, remembering that this is also can be rewritten as a negative, we get I times 4 over square root of 3 times 2 over square root of 3 times 2 over square root of 3. Okay, and now what's great about this is that that and that will go away. Perfect. Now we've got a lot of negatives, so what are we going to do? Well, remember, this is the same as saying negative 1 over square root of 3i. So this actually can become positive. So positive, these two negatives can become positive. Overall, we're left with I times sorry, with the negative I. Yeah, basically all of the negatives cancel. And this becomes, oh yeah, because I times I is negative 1. So we get negative I, sorry about that confusion, negative I, yeah, and also for here is the same reasoning. Not that this is an equivalent form. Sorry about the confusion. Because the i's became negative and then positive. Sorry about that, guys. Hopefully little inconvenience was caused. But anyway, what happens here is that this negative and that negative cancel. This I and that I cancel. And we're nearly done. Combine all of the brackets, we get 2 times 4 times 2, which equals 16, over square root of 3 cubed, which is 3 square root of 3. Okay? So overall we're left with 16 over 3 square root of 3. And because it's the exact same here, (16) over 3 square root of 3. And now, I said it in the tricky integral, and I'm going to say it again. Dividing by a fraction is the same as multiplying by the reciprocal. So, dividing by 16 over 3 square root of 3 is the same as multiplying by 3 over 3 times square root of 3 over 16. So this square root of 3, that square root of 3 will cancel. That 3 goes on the top. So we're left with this, 3 over 16. Same thing here. We're left with 3 over 16. Oh my goodness. Oh my goodness. We're nearly done. And now, same denominator. This just gets better and better. 3 plus 3 is 6. And now, oh my goodness. This 3, that 6 becomes a 2. This 8 goes away. That 16 becomes a 2. 2 over 2 becomes 1. Boom. We're left with pi. I'll see you in my next video. Goodbye.